И прежде чем мы начнем, я хотела бы представить вашему вниманию членов нашего жюри. Дмитрий Макаров, компания «Кастинг». Айденбек Берикбосен, компания «Полиметалл Евразия». Таиржан Салыков, компания «Полиметалл Евразия». Юрия Черепанова, World Armstrong International. Мурат Сайдуакасов, компания «Центр Консалтинг». Спасибо большое. Итак, мы начинаем наш...
Здравствуйте, участники, здравствуйте, уважаемый жюри. Наша презентация будет проходить на английском. Прошу понятие презентации. So, good morning, everyone, and my name is Ernias, and my colleague Nurstan. We are from Nazarbayev University, master degree students, and today we are going to present geometallurgical modeling and its application to mine planning. So, this study was supervised by Dr. Madani and also by Dr. Erkan Topal. So, mainly our presentation consists of four main parts. They are geostatistics, geometallurgy, geometallurgical modeling, and mine planning. So, before starting our presentation, I want to set our problem. Conventional mine planning is based on the great variability, and this great variability mainly cannot predict the mineral processing optimization systems and energy consumption. So, this conventional mine planning also generated by the block modeling. But this block modeling come to science named geostatistics. So let's stop on geostatistics. Geostatistics mainly consists of three main steps. First one is to have a data sampling from boreholes, then apply some quantification methods to determine its spatial continuity, then create our block model. Then this block model can be applied to future mine planning. In general, these sample inputs has some specification. They are coordinates, lithology, and grades. But today we are stopped on the geometallurgical variables, such as RQD or crushing index. So my colleague will continue with geometallurgy now.
Now let's talk about geometallurgy. So what is geometallurgy? Geometallurgy considers not only cutoff grade, but also it considers such variables as geomechanical variables, which includes rock mass characterization and the crushing grinding index. Also, this geometallurgical variables has some metallurgical variables, which includes this composition of minerals, ratio of elements, so recovery of metal. So why is this geometallurgy is important? Well, first of all, it is very helpful in forecasting production, as well as it is useful in optimizing mineral processing systems. Also, it can be applied in mine planning, and even it can be applied in choosing proper size equipment.
So let's proceed to the geometallurgical modeling. In general, this modeling requirement requires two things. It is the core samples coming from the boreholes and the modeling algorithm. This modeling algorithm can be non-linear or linear. So, for the example, linear can be creating, for non-linear can be simulation methods. such as sequential Gaussian or turning back methods. And discuss the difference between these two simulation methods, we can conclude that nowadays the simulation methods are better than the Kriging because it gives us better results and has no smoothing effect. But as you can see in the first figure, you can see that it has some smoothing effect and not produce the original variability, and results can be biased. So the application of simulation methods can give us the following benefits you can see in this slide. It can calculate the risk, then classify the resource and reserves, do optimal pit design, do also mine planning, grade control, and data reconciliation. But also simulation has own some methodologies. They are independent simulation and co-simulation. So when we have two variables and they have some good correlation between interrelationship, the co-simulation approach shows that it gives us the better results because it uses some cross-variogram and direct variogram, whereas the independent simulation uses only direct variogram. So procedure of the co-simulation method consists of four main steps. First of all, when we have, for example, two variables and it has some good correlation, we must transform this data to normal score, then conduct some variogram analysis, then simulate. After that, we can back transform to But the main problem of this co-simulation method is when we have some interrelationship between variables. For example, in this case, ferrum and aluminum oxide, we have some complex figure here in first diagram. Then when we transform to the normal score, which is the first step of the simulation method, it not produce some multi-Gaussian relationship that you can see in the last figure, this elliptical shape. In sum up all these pictures, we can say that if we conduct co-simulation method, it will fail. So the following complexities can impact the simulation, such as heteroscedasity, nonlinearity, and geological constraint can impact on our co-simulation, and the results can be not acceptable. So let me give an example for this from study. When we apply co-simulation simulation conventional methods, in this case for magnesium oxide and silicium oxide, the blue ones is simulated data, and as you can see, it is disseminated. So we can say that it not reproduces the shape of correlation, and the results will be biased. But there is a methodology named as a projection pursuit multivariate transform, and the idea of this transform technique is to decorrelate this normal score data to some space in order to simulate it independently. So it means that we can not use this correlation, intercorrelation between variables. So for the example of PPMT procedure, for the difference from co-simulation is PPMT has a transformation technique of normal score data to multi-Gaussian before the simulation. So after that, we can independently simulate this PPMT result, transformation, then back transform it to original space. And as in these pictures, you can see that the original data simulated and reproduce the correlation and the distribution. from the previous mentioned example, we can conclude that when we use the PPMT, it gives us results which are complete agreement with the original data. The blue ones is simulated data, red ones is original data. So by comparing, we can finally conclude that PPMT is much more better than in case of some complexities for future mine planning.
So now let's proceed with the application of the methodology in mine planning. Before going to the mine planning, we've first of all collected data, and based on this data, we've constructed our block modeling by using this PPMP technique. So then we'll proceed to mine planning, and finally we'll schedule our production. So before proposing our methods, I want to mention several issues in conventional methods. These conventional methods that are currently used in mining industry is only based on the cutoff grades and the Lersch-Grossman algorithm. So, but the method that we are proposing is not only based on the grade variability, but also it has some another geometrical variables such as RTD or NMR. So, this conventional mine planning method can be very helpful in calculating NPV, production scheduling, and the pit optimization. Whereas our proposed mine planning method is helpful not only in these three factors, but also it can optimize mineral processing plant, it can forecast our production, and also most importantly, it can reduce our energy consumption. So now in this slide you can see the example of application of the geometrical variables in mine planning. So now let's take two blocks with, firstly, block A has high copper grade with excellent rock quality. So consequently, the work index is much higher than block B, which has lower copper grade and a poor rock quality. So based on this work index, we can calculate our energy consumption by using this formula, and after calculating our energy consumption, we can calculate our revenue, since we know our income and our cost. So it's a rough example. So from this example, I want to conclude that considering of the geometrical variables is very helpful in calculating revenue. So to conclude our presentation, firstly, we've used transformation techniques for the complex data set. Then we've used these geometrical variables in mine planning in order to reduce our energy consumption, and also it was also helpful in optimizing mineral processing and production scheduling. So here's our reference list. Thank you for your attention. If you have any question, you can ask.
Спасибо большое. Будут ли вопросы у членов жюри?
Ребят, спасибо большое. Вопрос следующий. Можно ли предусмотреть процедуру обратного пересчета reconciliation? То есть отработали модель, переработали ее и обратно пересчитать, проверить расчет.
С новыми данными, да, вы имеете в виду?
Да, конечно.
Да, можно, естественно.
Каким образом?
Получается, новые данные опять будут импортироваться в модель, пересчитываться, а затем уже, основываясь на результатах, мы можем опять перейти на планирование горных работ и так далее.
Юлия?
Я хотела бы поблагодарить докладчиков. Было очень приятно, во-первых, услышать уровень английского языка, который, возможно, в вашем университете преподают. Конечно, это очень важно для современной индустрии. Было много сказано про геостатистику, то есть нам, в принципе, показаны очень глубокое, хорошее понимание геостатистических, статистических методов. И, наверное, вы нас убедили, что нам стоит рассматривать метод гауссовского распределения для решения наших проблем. У меня такой вопрос. Проводили вы, я тут по-английски спрошу, have you done a sensitivity test of a result for different parameters?
In this presentation, we consider the already done
Вы можете
study.
мне по-русски ответить?
На самом деле, эта презентация была сделана на основе уже проработанных данных, и их точность и так далее тоже проверялась, но она здесь не указана. Если вы пройдете через по ссылке, которые в этом референс-листе, то там есть...
Хорошо, вы можете его примерно сказать. Вот sensitivity тест — это, в принципе, когда мы меняем каждый параметр, входящий в систему, ну, например, на 5 или 10%, и смотрим, как меняется итоговый результат. Мне вот интересно, насколько итоговый результат, то есть был ли такой тест сделан вами?
Нами не был сделан, но научные исследования, которые мы рассматривали, там было сделано. Получается, они проверяли, и результат был не больше 5% разбросан.
То есть вы не можете сказать, от какого входящего параметра результат больше всего зависит?
Нет, мы можем сказать то, что он прямо пропорционально зависит от входящих variable, да, допустим, первый и второй, да, но он может быть изначально иметь хорошую корреляцию, может иметь хорошую корреляцию, но иметь слишком разбросанную distribution, да. От этого тоже будет разница, но так как данных таких мало, в принципе, научные исследования тоже не провели такой глубокий анализ, и как бы мы слишком чуть-чуть некомпетентны делать вот эту работу. В будущем, наверное, мы сделаем, но сейчас мы не сделали, и нужно дополнительные знания.
Спасибо большое.
Спасибо. Будут ли еще вопросы? Вопросы у зала? Спасибо большое. Итак, следующее выступление. Нурасыл Баталгазы, Назарбаев университет.
Спасибо. Добрый день, дорогие жюри, коллеги, гости. Тоже сегодня буду презентовать на английском, и прошу использовать наушники для перевода. Okay, good morning, dear guests. My name is Nurasıl Battalgazı. I'm currently a master's degree student at Nazarbayev University at School of Mining and Geoscience. And today I would like to talk about multivariate geostatistics and its application for optimization of NPV, net present value, in open pit mine design. And my supervisors are Dr. Nasser Madani and Professor Suvarnani. And the outline of my presentation is as follows. First of all, I will give some general overview about open pit mine, and then I will set several problems related to that, and then we're gonna talk about the methods to eliminate this problem, why we need this method, and how we're gonna apply this method for solving this problem. So at the end, if you will have any questions, I will be glad to answer them at the end. So first of all, in open pit mine, the pit shell design is mainly based on the constructed block model. This block model can be constructed or produced by two methods. One of them is estimation, and the second one is simulation. As you can see here from these illustrations, this is a pit shell, and you can see the block model. So, the main problem with the block model. If we are thinking about the reliability of the block model, constructed block model, we will have some results that can be negative or positive. So, if the block model is not reliable, we will have some negative consequences, such as bias in recoverable resource. It means tonnage, mean, grade, bias in cash flow or NPV of the project, bias in the geometry to select the optimum pit shell, bias in mineral resource and ore reserve classification, and bias in mine planning, long and short-term mine planning. So, as I mentioned, we have two methods called simulation and estimation. Based on papers and the best practice, we can compare them, and this is the comparison list of these two methods. As you can see, simulation produces many multiple realizations, while in estimation you can provide with only one unique realization for each block. In simulation, you can assess the uncertainty, while in estimation you cannot produce the local uncertainty, as my colleagues said before. In simulation, you can work with extreme values, while in estimation, you cannot work with these extreme values. And the main privilege of this simulation method is that it can produce the original variability. However, in estimation, you cannot produce the original variability. So based on this comparison, we can state that simulation is better than estimation. So the next slide shows some examples related with the estimation and the simulation methods. Here we can see the estimation method for the iron. You can see we have a smoothing effect. This smoothing effect actually decreases the variance, while in simulation we don't have this smoothing effect. This is another example. As I said before, simulation produces multiple realizations. In estimation, it's provided with only one realization. So if we constructing the graph of grade with the year, the average grade with the year, the black curve shows the response of simulation, the average realization, and red curve shows us the response of estimation. As we can see from this graph, the response of estimation is very fluctuating. It has a high fluctuation at the beginning, so it's not actually good for the results, while in average of response of realization for the simulation is changing gradually. So another issue occurs when we are thinking about the correlation between the variables. Like questions that can this method produce the same correlation? Can this method provide the shape of correlation, or can it work with the compositional data? So as you can see, we have two maps of the two methods called simulation and independent simulation. This simulation can be divided actually into two, like co-simulation and independent simulation. Here we can see that despite the fact that you can the difference between the maps is very significant. Actually, this little difference, for instance, for the magnesium oxide, for example, at these points we have a different concentration of magnesium oxide. For instance, here we have a higher concentration. In independent simulation, we have a little bit lower concentration. This little difference can lead to millions of dollars of loss or gain. So this is an example of the co-simulation and simulation methods, independent simulation. This is the original variability of ferrum and magnesium oxide, as you can see. And the independent simulation, despite the fact that it can reproduce the correlation, it cannot reproduce the shape of the correlation. As you can see, it's very different. However, in co-simulation, it can reproduce the correlation in the shape of correlation. As you can see, they are almost the same. So by using co-simulation, it will lead to reliable resource model rather than independent simulation. So this difference can lead to results of different pitch shell design. Another problem is dealing with compositional data. For instance, if it is of interest to simulate or estimate the minerals in the deposit, for instance, iron deposit, we will have some minerals like hematite, aluminium, and silica. And this is an example of the sample. As you can see, the data taken from the drill holes will sum up to 100% for each sample. So, but co-simulation, the main problem of the co-simulation that it cannot reproduce the 100% summation of the elements in one block. So the co-simulation cannot reproduce the restriction of sum up to 100%, which is not appropriate result. So the solution for this problem is to use a log ratio transformation. By using this log ratio transformation, the application is as follows. First of all, we will transform it to the isometric log ratio values, and then we will simulate. And after simulation, we back transform it, and then we will have results which will sum up to 100% for each block. So application of this co-simulation in mine planning. First of all, just to see the comparison between the estimation and simulation, I'd like to start with the estimation method, the kriging. This kriging, as I said, will provide with one realization, and this one realization will give us one constructed block model, and this one constructed block model will give us one pitch shell design. This is because of that it's very biased because we have only one result. So one block model and one result of the production schedules, one result of final pit characteristics, right? Rock tonnage and ore tonnage. In co-simulation, in case of co-simulation or application of log ratio transformation for compositional data, the co-simulation reproduce the multiple realizations. For instance, we have multiple realizations. Here we are given with 8 example of the realizations. So these 8 realizations will give us 8 different constructed block model. So and 8 different pitch shell design. So this 8 pitch shell design will give us different NPV, different ore tonnage, and different results. So by constructing the NPV value on a graph with the ore tonnage and the waste tonnage, we can identify the most optimum pitch shell in open pit mine. So this is but it should be the same sequence in mining of the ore body. For example, Lurch-Grossman algorithm, same set production rate, mill capacity, and other factors that affecting the pit. So we can identify the most highest NPV. So by using co-simulation, we will have some range of results. For instance, we can give worst scenario, best scenario, or average of scenarios. So we will have like different NPVs for different realizations, and it is actually good for investors or mine planners to make some uncertainty in scheduling, uncertainty in grades, or uncertainty in NPV. So it will be very important for the investors. So by using co-simulation, we will have some positive consequences, results, like better assessment of recoverable resource. We can select the optimum pit design, better assessment of NPV, better risk analysis, and better mine planning. And it will be very useful for the mine planning to better determine the probability of meeting given production target. So this is a reference of my presentation, and if you have any questions, feel free to ask me. Thank you.
Спасибо. Будут ли вопросы у членов жюри? Юлия?
Здравствуйте. Я еще бы раз хотела поблагодарить за хорошую работу и, безусловно, очень важную задачу поиска наилучшего метода моделирования наших данных. Вопрос общий. Вы случайно для своего просто интереса они делали сравнение для данных, которые получаются в этих двух методах вне точек с данными?
Да, мы делали, у нас есть программа, ISATIS называется.
И какие результаты?
То, что co-simulation лучше, чем independent simulation.
Мне на самом деле просто интересно, потому что в тех местах, где у нас данные есть, а в реалиях у нас ситуация, что данные очень разбросанные, иногда расстояние между данными достаточно большое.
Да, также зависит от этого.
Что не происходит ли увода результатов в экстремальные значения между точками с данными? Потому что кригинг в тех местах, где данные есть, он тоже работает неплохо.
Да, плохо работает. Но, скажем так, если корреляция между variables у нас плохая, то можно использовать co-simulation для того, чтобы сравнить симуляцию и данные, которые у нас есть.
Ну, а вот в точках между данными, вот эти оба метода, как они разнятся слишком? Что происходит вот в местах, где нет данных?
Да, понял. У нас есть разные constraints. Получается, может быть inequality constraint, когда один variable больше, чем другой. Тогда, получается, мы можем использовать co-simulation для того, чтобы воспроизвести именно ту корреляцию, которая нам нужна. То есть мы можем воспроизвести корреляцию, которая есть. Основываясь на этих корреляциях, можно сделать вывод, то, что co-simulation лучше, чем...
Конечно.
Одну секундочку.
Просто если учитывать места, где нету данных, то мы задаем какой-то определенный радиус. Получается, в этом радиусе мы знаем то, что здесь будет оптимальный вариант для нашего ошибки и так далее, да? Но если симуляция будет превосходить этот радиус, она просто нам даст как бы unknown results. Нам как бы будет советовать сделать дополнительные borehole sampling, да, и чтобы точно знать и уменьшить ту или иную ошибку в будущем. Но, в принципе, программа может, если мы увеличим радиус, она может дать результаты в соответствии с корреляцией и так далее, да? Но она также будет давать другую картину, где будет указываться то, что там наибольший риск, то, что мы имеем ошибки, большой процент ошибки и так далее.
И по вашему опыту, какой метод симуляции, какой метод, статистический метод, чаще всего выпадает за ваш оптимальный радиус? Вы оба метода сравниваете, просто вот какой из этих методов чаще всего сидит в радиусе допустимых значений?
Если у нас есть два variable с хорошей корреляцией или хорошей distribution, то co-simulation лучший метод. Но, естественно, мы сейчас везде утверждают то, что, и мы тоже с этим согласны, то, что симуляция сама по себе лучше, чем кричинг, потому что кричинг нам дает результаты, не дает результаты на максимальных значениях, и наоборот увеличивает минимальные, получается, результаты, не учитывает некоторые минимальные результаты. Из-за этого у нас получается картина такая более-менее гладкая. А в случае симуляции мы имеем четкую картину, и где у нас большие значения, там большие значения и так далее. Если вот сравнивать три метода: independent, co-simulation и crunching.
Спасибо. Будут ли еще вопросы? Спасибо большое. Итак, мы переходим к презентациям Казахстанско-Британского технического университета. И приглашаются Адина Аймухан и Аида Кеншимова.
Доброе утро, уважаемые дамы и господа. Наша презентация также будет проходить на английском языке. Dear jury, participants and audience, we are fourth-year students from Kazakh Bridge Technical University, the Faculty of Geology and Oil and Gas Industry. And now, today we're going to present you our project called New Method for Express Characterization of Productive Formations, and improved hydrocarbon and ore recovery using advances in hydraulic fracturing, in situ leaching for mining and petroleum operations. Here is the agenda for today. We're gonna be talking about the CBM and then our theory concerning the ISL, which is in situ leaching in the uranium. So, as you may know, the CBM is one of the high-performance energy sources which is considered as a green economy, which is widely introduced for the Kazakhstani nation by our president. And here on the picture you can see the main sites, like most resources of CBM. It's mainly the Russia, China, and Australia and USA. But as for the Kazakhstan, we have the Karaganda coal basin, which is also one of the biggest basin for the CBM. As for geology, due to the time limit, we decided not to go through all the geological structures in it, but what is meant to say, here you can see the Karaganda coal basin and mainly the Cherubay-Nora region, which where the samples we worked with came from. Here is the coal cores and some samples from the shafts. And the Karaganda coal basin is basically described by the high gas content, very
sun, and exactly the Karaganda coal basin, we see that the permeability is less than 0.1 millidarcy, which is the lowest value in this table. So we use the hydraulic fracturing in order to extract the methane from the coal seams. You may also know what hydraulic fracturing is. Basically, we drill the well, then we, by the well logging, we find out the coal seams and fracture these coal seams. Then we inject the fracturing fluid with the propellant in it. Then we pump it up again, and the propellant that is left inside will stay there and keep the fractures open in order to extract the methane. So, in this region, the hydraulic fracturing was performed, but unfortunately it was not successful. So the main course and the main aim of our study was to solve why is that, why the hydraulic fracturing was not successful in this region. First of all, we thought maybe the gas content was not high enough, but we studied all of the reports from this coal seam, and we found out that the gas content in this region is up to 99.6%, which is very high, and the Karaganda coal basin is known for that. So it's fine at this point, it's not the issue. The next point was the inadequate poor choice of the perforating intervals for the hydraulic fracturing. So we studied this issue. We performed laboratory measurements. We measured the magnetic susceptibility and permeability for the samples from the coal mines and for the core samples. Next slide. So as for the results, here you see the measurements that were taken across the coal seam, coal layer. The direction of the arrow shows the direction in which the measurements were taken. So here's the graph with the magnetic susceptibility and permeability. Due to the fact that we go through across the layer itself, we see no correspondence here. The next sample was taken. We take the interlayering of the coal in the middle, as you see, shining one, and we see the great correspondence of magnetic susceptibility and permeability measure values in here. The next slide. And for the next sample, we also took the interlayering of the coals, but of the great values. So we found out that there also was the great correspondence of the permeability and the magnetic susceptibility values. And for the core samples, as you may see in the picture, hopefully it's seen, the fractured regions with the great permeability correspond with the high magnetic susceptibility values in the sample C2K, but not for the C1K, due to different types of the coal seams and the rock itself.
Thank you, Aida. As a continuation of our study, we decided to look for some other methods for other resources with the same nature, and we found out that the uranium, which is also the one source Kazakhstan is very well known for, it's basically the second, it's the leading producer, but the second in terms of reserves. As you may see, here is a picture which describes and represents the countries with the highest uranium reserves. Australia has over 1 billion, and the second, darkest color represents the Kazakhstan, which means we are also very luckily having a good amount of uranium in there. And as for the method we are recovering our uranium, it's called the ISL, which is in situ leaching method. The in situ leaching method is basically works as we are injecting the solution into our uranium-bearing sand, and then as the solution dissolves all the uranium, we are taking out the pregnant solution and then sending it to the uranium like a processing plant. And as for the method itself, about 48% of all the uranium reserves in the world are recovered by this method, and the Kazakhstan, in terms of ISL, produced about 22,000 tons, and it's about 37% of the world total. Beside the Kazakhstan, the ISL is also widely used in Canada and Australia. So the reason we've decided to include this theory in our study is that the magnetic susceptibility correspondence with the permeability can help to identify the highest permeability zones for the ISL. Like the ISL's effectivity will increase if we will send our solution to the zones with the highest permeability. And currently it's only like in the theory stage, as we are going to find the ways to test the samples and get the measurements of a real sample set. Oh.
Thank you, Adina. And as we come for the conclusions, for the CBM part, the method of using magnetic susceptibility characterization will lead to the finding out the so-called sweet spots, the regions with the high gas absorption zones and total organic content. Then it will increase the effectivity of the hydraulic fracturing as we find out the more permeable zones in order to frac them. Then, due to the more accurate permeability measurements, which is more suitable hydraulic fluid and propane types, we studied this region and found out that the most suitable one for the Karaganda Basin was the foamed or energized systems and polymer covered sand as a propellant. And for the ISL, it's just our theory, but nevertheless, we think that according to our previous studies and lab measurements, we assume that we may find out the most permeable zones for ISL in order to increase its effectiveness. Thank you.
Спасибо большое. Будут ли вопросы у жюри? Юлия?
Я бы хотела, во-первых, опять же, поблагодарить выступающих за их интересный доклад. Наверное, простой вопрос. Сколько образцов вы проанализировали?
3 образца с coal mines, и у нас были различные коулы. Наша задача была, получается, коры. Наша задача была именно выбрать те образцы, где сохранились длинносные.
Мы исследовали 3, получается, ящика кернов, проводили исследования с помощью пермиометра и магнитометра для лабораторных исследований. То есть это на кернах производилось. Вот.
Спасибо.
Можно, да? А скажите, пожалуйста, а почему вы выбрали именно эти 2 метода? Почему среди множества? Магнитометрию, да, и вот как вы назвали? Потому что я знаю, что корреляции вот именно у углей там есть еще по соотношению ионов там, металлов и прочее. Почему именно эти 2?
Так как мы опирались на исследования, ранее произведенные нашим супервайзером, нашим профессором Ивахненко, и он находил некую связь между магнитной восприимчивостью и проницаемостью. И здесь мы уже делали удар не только на исследование проблем гидроразрыва, но также на применение именно этого метода в исследовании.
Спасибо большое, весьма интересный доклад. Спасибо.
Спасибо большое. Итак, последняя презентация на сегодняшний день. Алишер Саудов, Казахстанско-Британский технический университет.
Раз. Okay. Good morning, dear guests and participants. My name is Alisher Sadov. I'm studying 4th year bachelor's degree geology at Kazakh British Technical University. And today I want to talk about the identification of geological structures using mathematical equations in interpretation of magnetic survey data. In a nutshell, I had a magnetic survey data which is printed on map, and I did various of methods for filtering and for the interpretation of this data. But first of all, let's come to the studying area. Here's look at that rectangle, small red rectangle. It corresponds to the studying area. It's located just near to the lake Balkhash. Here is the highway, and also the Mineral and Akbakai villages are at 10 and 15 kilometers away to the north and to the west. Okay. So here is the working process. This is a magnetic anomaly map, which is printed on a paper, and then I digitized it on a surfer program in a dot format. In order to convert this data into the WASIS montage, I converted to the DGB format data. As a result, I've got these pictures. Here's a magnetic anomaly map. It is a 3D representation of that data. It's a view from the down left side. So this map is conducted by a UNI party. It's very old data. So the scale is 1 to the 200,000, and list is L43 and 26. So the first method and the first filter that I used is a reduction to the pole. So the meaning of that filter is, initially the magnetic field has two components. It is X and Y components, and our main purpose is to eliminate the X component in order to make this anomaly straight over the body. But in order to make this operation, we have to know the inclination angle and declination angle, and those parameters can be known using other programs or internet. So if we compare the first map, it's a magnetic anomaly map, and the reduction to the pole map, here's you can see the small difference. This map is shifted a bit in this side. So it's actually the map that I was working with in the next slides. So the next filter that I used is a horizontal derivative. I used the first order derivative in the x direction and in the y direction. Then, using this formula, I've got the total horizontal derivative. It's like using this formula. It's quadratic equations and under the root. So, if we look at that picture, we already can see that the structures are already known and already can be seen. This is a next filter. It's a tilt derivative method. So the tilt derivative is actually relatively very modern and very new method. Here it's a more exactly can be seen the structures here. If we compare the tilt derivative filter and total horizontal derivative, we may see the huge difference. The difference in the quality. So here is the quality is much better than here, and we here can see the exact structures. So this is a total horizontal derivative of tilt derivative, or in other words, it's the second derivative. It gives us the map in more detail, and it's the shallow structures which are located near to the surface. This is an upward continuation filter. So the main name of that filter was to determine the regional effect of the deep structures. So you see that the map is very smooth, and it corresponds to the very deep structures which are located very deep. So this is a comparison between upward continuation filter and RTP map. So here we also can see the difference. If you look at that regions and in that region, you may see that those regions correspond to the shallow structures, and that region corresponds to the very deep structures. This is a downward continuation filter. So we artificially move our measurements to the down, and you may see here in a red color corresponds to the shallow structures. If we then compare those two maps, again, shallow structures on the red side, and here, this region, and also this region, it corresponds to the shallow structures. So this is a pseudo-gravity field map. It is a correlation between gravity map and magnetic anomaly map. It's between the density and magnetic susceptibility. Here you see the units, it's in milligauss, but also we have to know the density contrast between the rock types. We have to know geomagnetic inclination. And we may conclude from this map that the red color is correspond to very high density region, and maybe some deep structures are located there. So the regional field, if we compare, so the upward continuation is pseudogravity map, the regions with the red colors, look at the left downside, it corresponds to some maybe deep faults or some other structures, very deep structures. A bit of geology. So the thing that you have to know is that the major faults are located in that region, and also the Devonian granites and granodiorites of the Middle Age, also the early Hercynian granites, halorite, cerussite, schists, sandstones, conglomerates are located here. That is a scheme of the main faults. It is not my region, it's not corresponds to the scale. So my region is here, but you have to know the main faults which are located there. So the 1, 2, and are Jalir-Neyman faults. Number 3 is Sarutum, and number 10 and 11 are West Balkhash and Balkhash faults. This is a tectonic division. Okay, next. So the detection of faults. So in my previous slide, in my previous interpretation, I've got the results from the tilt derivative map. This corresponds to the faults. And if we compare those two maps, they are almost coincide with each other. They are very similar. And this gold deposit maps of a certain company, картами золоторудных месторождений. То есть это моя территория, it's my region. So the gold deposits which are located in my region are Karatas Bereg, Burumtas, Ashek, and Akbakai, of course. On the left side, the west to the west, Kenjem, Altentas, and Burumtas. So this comparison, of course, between the Gaussian residual MIP and a downward continuation. So if we look at the previous map, those red circles correspond to the already known gold deposits, and the blue circles corresponds to the perspective areas for the gold. This is the Voxy model that I've constructed. The magnetic susceptibility is between this range. And this is a Voxy model and plus ISO surfaces. So here, these regions corresponds to the very high magnetic susceptibility regions, and this area is very perspective, and also the deep faults are located in that region. So gold ore and faults correlation. So it's my result. I found out that the gold ore deposits they are located near to the faults. So again, the red circles corresponds to the already known gold deposits, and those blue circles is very perspective deposits that I got in my research work. So the conclusion, it's proven that it's very effective methods of interpretation using mathematical equations. And as a result, we've got the measured fault zone and very perspective zones of the gold deposits. Also, intrusive related golds is generally hosted in granites, porphyry, or rarely dikes. It's a it's rocks where the gold usually are located. And it was observed the correlation between faults and gold ore deposits. Thank you for attention.
Спасибо большое. Будут ли вопросы?
Алишер, большое спасибо, интересный доклад. Мне вот эта тематика тоже очень близко, потому что я занимаюсь поисками, наша команда занимается поисками и золоторудных месторождений, и полиметаллических, и в первую очередь геофизические методы для нас важны, то есть важны как поисковые методы. И тут больше практического значения хотелось бы услышать, может быть, где-то в кулуарах с вами переговорить, потому что весьма интересная область обработки данных геофизических, это математическая обработка. Тут немножко такой, скажем, провокационный вопрос к вам. Вы готовы дать голову на отсечение, вот когда вы положили кружки, и сказать: привезите сюда буровую, пробурите, и вам будет месторождение?
Ну, если вы, наверное, заметили масштаб, да? Там масштаб очень такой мелкий. И поэтому я выделил только очень перспективные, как сказать, areas, да? Как называется? Участки.
Ну, правильно я понял, что это где-то ранг рудное поле,
C1,
да?
может, C1, там...
Ну, пока еще, наверное, до C1 далеко, это еще прогнозные ресурсы, да? Другое дело то, что если выделяются аномалии, аналогичные месторождениям аналога, как вы показали, то, в принципе, вы можете доказать модель, которая работает на неизвестных участках. Это можно так сделать?
Ну, в общем, мы с моим научным руководителем говорили об этом, и вот пришли к выводу, то, что в Фоксе модель же вы видели только что, с 3D, когда крутилась картина. Вот, если мы, допустим, возьмем рейндж магнитной восприимчивости в каком-то месторождении, допустим, которое находится близко, допустим, к Акбакаю, и возьмем этот рейндж, применим сюда, и, возможно, то есть у нас один участок, и в этом участке, возможно, одинаковые условия залегания были, одинаковые условия, получается, магнитной восприимчивости. Если мы знаем магнитную восприимчивость Акбакая, то и применим сюда, то, возможно, мы, так сказать, выделим какие-то перспективные участки здесь.
Хорошо. Тогда последний вопрос. Да? Значит, это вот более-менее региональное поле, насколько я видел, да, по масштабу. Мы можем ли ваши методы математической обработки геофизических данных применить на локальные участки?
Да, на локальных еще лучше было. Просто
то есть
не было
мы вам
данных.
дадим дрон с магнитометром, вы приедете на наш участок, залетаете, получите данные через 3 недели и можете применить свою модель и показать нам, где бурить.
Можно попробовать.
Говори «да». Да.
Да. Да.
Большое спасибо.
Спасибо.
Спасибо.